In this episode, Joe Rogan and his guest discuss the 10-year-old genius who cracked the code on the multiverse.
Night and smoking, I went on a little YouTube wormhole situation, and somehow, but I wound up on this video that was like, world's smartest kid thinks that CERN blew the world up in 2008. All right. And I'm like, what the fuck? So I go on this video, right? And I'm watching this video, dude. And it's this young kid. He's like 12, and the motherfucker's talking. You know, you got to invest like 20 minutes into this kid talking about things that are super smart. And it's kind of like to show you he's super smart. You know what I mean? This kid. And his dad's doing the recording, I believe, or a relative, somebody very close to him. And he goes into this whole theory of how he thinks when they collided the electrons, I believe, in the super collider, CERN, that they caused some crazy chain reaction that blew up the universe, but they also they created an atom that weighed too much. And the first 20 minutes is also explaining infinite parallel universes. So what the kid winds up with is this theory of like, one atom weighing too much and is that being just enough to shift our universe into a parallel universe. Yeah, this is it right here, dude. So this kid had me fucked up, because after I watched this, everything I saw for months was talking about, like, it would be a news guy on the news, like, I don't know what universe I'm in anymore, or is Spider-Man into the Spider-Verse, like everything I saw for like 4 or 5 months after watching this video was like multiverse shit, like shit about multiverses, and it's got me fucked up, Joe.
I hear you. I'm fucked up too now.
Fucked up, man.
Read this kid. Look at what it says there. He claims that CERN destroyed the universe during recent experiments, which has resulted in us living in a nearby parallel universe instead.
But that means that there's an infinite number of parallel universes in our multiverse. And there's an infinite number of these realities. And in each reality, as every electron spins an animator of an animator to an animator to an animator around a nuclei of an atom, we're catapulted into, an infinite number of alternate universes. Just imagine this is the start of the universe. This is our original timeline, right? But as soon as this starts, we are infinitely catapulted into an infinite number of parallel universes.
And so that led me to this idea of the simulation point, which is a kind of technological singularity. But then I started to research things like quantum physics and some of the mysteries around, the observer effect and quantum mechanics. And then I started to look at all the world's religions, and I realized that they're all kind of saying the same thing, which is that there is no physical universe. And so, that led me to the conclusion that we are most likely inside some kind of a computer simulation or a massively multiplayer video game, depending on how you look at it.
But where did that simulation come from if we are inside of it?
Well, that's the big question, right? And there's two versions of simulation theory. And, I teach a class on this at Arizona State University. It's probably the first college-level class about simulation theory, and it kind of pulls in science fiction, religion, philosophy, and technology. But one of the key distinctions I tell my students to make, because it's not talked about a lot with simulation theory, is what I call the NPC versus the RPG versions of simulation theory.
Okay.
Right. So NPC, as you probably know, means non-player characters within video games. So those are the AIs in the video game. The bartenders, the people you're beating up, the opponents, all of that stuff. But basically, they're just code and they're AI. Then there's the RPG version, which is that we are actually doing a role-playing game, right? So you exist outside the game, and then you have a character or avatar inside the game. So it's just like what we would consider an MMORPG today, right? Except with more sophisticated technology. And so in that case, you get a little bit of a different answer than if you talk about an NPC-only type of simulation, right? Because that's just running on a computer, and we're all AI in that case. Now, the two aren't mutually exclusive, right? In a video game like Fortnite or whatever, World of Warcraft, you have NPCs and you have PCs or player characters, right? So you've got both of those things going on. And so depending on how you look at it, you might come to different different answers about who's outside the simulation, which would answer the question of who made the simulation, right?
Yeah.
So in the first case, you basically say that if we can get to the point where we can build these simulations, what I call the simulation point. So I call that a kind of technological singularity. Now, we've heard the term singularity mostly because of AI and super intelligent AI, right? And AI is going to take over the world. But the guy who defined the term was actually a computer scientist who became a science fiction writer named Werner Vinge. In fact, he just passed away like a month ago or something. He was a real pioneer in science fiction and the cyberpunk kind of subgenre or so. And so he said the singularity happens when technology increases exponentially to the point where everything will be different for humans after that point.
I entered, I think, into the multiverse.
Whoa! Now, as a scientist, you realize when you say something like that, you open yourself up to ridicule. Do you feel hesitant to communicate these ideas?
Well, to a degree, yes. But, I'm 62 years of age, and, at one point, I just don't care. I just don't care, This is true. This happened to me. And I can push the envelope on these ideas because the credibility of my research is well established. I can save the bees. Do you care whether I have taken psilocybin mushrooms, if I can save your farm, your family, your country, or the world billions of dollars and protect biosecurity?
I care more.
I care more. That's right. Yeah. So I'm telling you things. I'm not making these up.
I don't think you are.
I don't have to.
I just wondered.
But just because you can't explain it does not mean it's not true.
Right.
And I think that we need to accept the fact that the reality is not limited to the perception that we have traditionally used.
Apparently a bunch of people who think Mandela died in prison.
Right.
And there's, as far as I know, he was released, became president of South America. And that's the universe I'm from, just personally. But it's crazy, dude. Because it's not just this video. It's like you watch it, and that YouTube algorithm starts sending you down a whole bunch of other. You start hearing and it's like and then again, everything that came out, there was all these shows I would see or movies or news things about the multiverse. All of a sudden, was everywhere around me. It was fucking nutty, dude. So I'm fucked up about that shit right now.
Well, if there was something they could do, that might open up a door to a parallel universe. You don't think they would do it?
Stranger Things, you mean?
Yeah.
Say that's
this
the goal.
Is Stranger Things. I mean, things are strange, right? It is Stranger Things.
Bizarro world. You
know what's the weirdest one? Is the people that dismiss climate change. That is the weirdest one to me. So I'm like, I'm trying to figure out what's the benefit of dismissing climate change, other than if you work for the oil industry or something.
Well, Iceland just lost a glacier.
Yeah.
They just posted a whole thing of 10 or 80, something in the 80s, a glacier picture of it, and just now, and it's gone.
But I'm not even saying blaming anybody for it. I'm saying dismissing it as an issue. I'm like, let's pretend that people have nothing to do with it. I wish people had nothing to do with it. Because then we can go, holy fuck, it's getting hot. How hot is it going to get? You've done an amazing job in this book of trying to boil it down for dummies like me, but it's hard. It is a complicated and insanely nuanced subject.
Yeah.
And it's one of those things where it like this many worlds theory, for one example, the just the possibility that there's explain that.
Sure.
Explain for people that don't understand what quantum mechanics even means. Give them just a little bit of that, and then explain many worlds theory.
Yeah, good. This is what I'm here to do. So,
thank you.
An electron, take an electron. Quantum mechanics should apply to the entire universe, but it becomes unmistakable when you look at little tiny things, right? So we always are talking about electrons or atoms and so forth. An electron has a position, and well, sorry, let me not even say that. Even that was wrong. It's just so hard to correctly talk about quantum mechanics, right? If you were Isaac Newton, before there was quantum mechanics, there was classical mechanics. And basically, quantum mechanics and classical mechanics are the only two big frameworks that have ever existed in physics. Classical mechanics was so good that everyone thought that was just right, and it was all a matter of filling the details until quantum mechanics came along and changed things. In classical mechanics, an electron is a point. It has a position, a location in space, and it has a velocity. It's moving somewhere. And from that, you can predict what's going to happen. Okay? Quantum mechanics says, no. The electron has a wave function. So there's a wave. Sometimes you hear this debate about are things like electrons and photons particles or waves. The answer is that they are waves. And the wave function has this weird property that when you're not looking at it, it's a wave, it's all spread out or it's localized somewhere, but it obeys an equation, the Schrodinger equation. So far, so good, just like regular physics. There's a thing, the wave function, it obeys an equation, the Schrodinger equation. You can predict what's going to happen next. But the weird thing about quantum mechanics is that there's a whole separate set of rules for what happens when you look at the thing, when you observe it, when you measure it.
That's where things get squirrely with people describing it, right?
Yes.
And that's where they want to go woo-woo on you.
It's an opening to be woo-woo, right? When you say, like, what do you mean observe something? Like, does it have to be a conscious being? Can it be a video camera? That's just weird, right?
Is it the act of measuring that changes things?
Well, this is the puzzle, okay? This is what is called the measurement problem of quantum mechanics. That the rules we teach our students at Caltech or anywhere else when we teach them quantum mechanics in their sophomore year of college, the rules say when a system is observed, when it is measured, its state, its wave function changes dramatically, suddenly, and unpredictably.
Now, let me ask you this. How do we know this based on if you're measuring it and it changes? How do we know? Because we didn't measure it before. Like, what observations are we making that we understand the state of it before it's measured without measuring it?
Good. There's a couple of ways. So let me make things even simpler. Forget about where the electron is located and think about the electron is spinning. Right? Okay. The electron is spinning just like the Earth spins. It's really exactly like that. It's like a little spinning top, except when you measure the spin, you can sort of send the electron through a magnetic field and it will get deflected either up or down, depending on whether it's spin up or spin down. You only ever get one of two answers. It's either going up or going down. It's nowhere in between. This is an empirical measured fact, okay? So that's a part of quantum mechanics. That's the quantum fact, that there's a discrete set of possible answers to this question. Is it spinning clockwise or counterclockwise? Yes or no. It's just those two possibilities, nowhere in between. So if you have a magnetic field that is oriented vertically, send your electron through it, it gets deflected up, you say, oh, it's spin up. So now I've measured its spin. Now I know what its state is. If I send it through another magnetic field, or oriented vertically, it will always be deflected up every single time. We know what it is. We're going to measure it. Measuring it, in this case, doesn't change it. It's in exactly that state. We know it, okay? Now let's send it through a magnetic field that is oriented horizontally. So it's going to be deflected either right or left. We know exactly what state it's in. It's spinning this way. But when you send it through that magnetic field that's oriented horizontally, it gets deflected left or right 50-50, unpredictably. There's no way we can predict it. And then once it is, so okay, now it's been spinning up, you measured its spin left, let's say, send it through another magnet that is going vertically. And now it's 50-50 again. It could be spin up or spin down. So somehow, even though we knew exactly what state it was in, we couldn't predict what would happen next. That is part of quantum mechanics.
Well, if there was something they could do, that might open up a door to a parallel universe, you don't think they would do it?
Stranger Things, you mean?
Yeah.
Say that's
this is Stranger Things. I mean, things are strange, right? It is Stranger Things.
Bizarro world. You
know what's the weirdest one? Is the people that dismiss climate change. That is the weirdest one to me. So I'm like, I'm trying to figure out what's the benefit of dismissing climate change, other than if you work for like the oil industry or something.
Well, Iceland just lost a glacier.
Yeah.
Like they just posted a whole thing of 10 or 80, like something in the 80s, a glacier picture of it, and just now, and it's gone.
But I'm not even saying like blaming anybody for it. I'm saying dismissing it as an issue. I'm like, let's pretend that people have nothing to do with it. I wish people had nothing to do with it.
AI starts to become super intelligent and it grows exponentially and everything will be different. But I think this idea of the simulation point where we can create simulations that are indistinguishable from reality. And I lay out like 10 stages in my book of all the technology we would need, including brain-computer interfaces like in the Matrix, right?
Or Neuralink.
Or Neuralink, right. We're getting there, right?
Yeah, we're very close.
We're at the beginning of that whole thing. And so that's stage 8, stage 7 and stage 8 on the way to the simulation point. And, being able to read, but also then being able to write memories as well. And then so the definition of the simulation point is being able to create a virtual reality that is indistinguishable from physical reality with AI characters that are indistinguishable from biological characters. So, you wouldn't be able to tell you're talking to an NPC, basically.
Right.
We're getting closer to that already, right?
Yes.
Yeah, I mean, there's like companies out there doing smart NPCs now inside video games.
Right, but what would be the difference between looking at what is possible in the future and making either a hypothesis or suggesting that has already taken place?
Right, so that's kind of the leap, right, that you need to make, which is to say that if we can do it, now let's imagine a civilization that was 1,000,000 years ahead of us, 1,000 years ahead of us.
Yeah.
Even 200 years ahead of us, right? But certainly 1,000 years ahead of us. So where will computers be in 1,000 years? They would already have created these types of simulations.
Right.
Right, because if we can do it, now 50 years ago, we didn't know if we could do it. We didn't know if computers could get to that point, right? Today, we're pretty sure we can get there. In fact, I'd say that I'm 70% sure that we will get to the simulation point, which means I think there's a 70% chance we're living inside a simulation.
It's not that we don't know whether the electron is spinning clockwise or counterclockwise. It can be in a superposition of both. That's just the spin version of the position of the electron can be spread out in a wave, right? It's truly not just that we are lacking some knowledge. It's that the knowledge really isn't there. And again, this is how we teach quantum mechanics in textbooks. And then I'm going to correct it because Many Worlds is much better. But this is the standard textbook version. There's a wave function. The wave function for a spin is it's either up or down or some combination. And then there's a rule that says when you measure the spin, you only get up or down. You don't see the wave function. Just like the cloud that you have for the electron's position, when you look at it, you see it at a location. So another way to make the same argument is take a little piece of, I have a nice little image of this when I give talks, a little piece of uranium. So it's a radioactive little chunk of metal, and you put it in a bubble chamber. So it is emitting radioactive particles, and you detect the particles. You can see a little streak of motion when the particle leaves the uranium, okay? Well, like I said, when you're not looking at it, this electron is supposed to obey an equation, the Schrödinger equation. And you can ask what the prediction is when a radioactive nucleus decays and gives off an electron. What is its wave function going to do? What is the wave function of the electron going to be? And the answer is it goes off in a spherical wave. It goes off in all directions at once.
Evenly.
Yeah. All directions evenly, but you never see that.
Is that roughly
always
based
see a
on the
line.
shape of the piece of uranium? Does it vary?
No, because the electron gets from one individual nucleus of an atom, right? So what the uranium is doing doesn't matter. It's just that one atom matters. And the easiest thing for the electron to do is just to go out in a sphere. It doesn't have to. It can go out in higher energy states. But the point is, it's not going out in a straight line. But when you look at it, you see a straight line, right? That's the fundamental mystery of quantum mechanics, that how we describe the thing when we're not looking at it is different than what we see when we look at it.
So when you're in pursuit of an understanding, a deeper understanding of quantum mechanics, when you're thinking about people from the 1900s that are just sort of basically getting the first steps going to understand this stuff, when you're talking about this lack of funding and the lack of encouragement for people to pursue quantum mechanics, you strongly feel like there are answers to these questions.
Yeah, that's right.
That we just need better tools and a better understanding, better equations, more time.
Yeah, me and Einstein think this, right? So Einstein is one of the secret heroes of the book because he has this reputation as someone who just couldn't quite accept quantum mechanics. The title, Something Deeply Hidden, is a quote from Einstein when he was talking about when he was a kid and he had a compass, right? And he was given his first magnetic compass and he could rotate it this way and that way and it always pointed north. And you and I would go, that's cool. But he was Einstein. He's like, wow, this is amazing. Why? How does it know where north is, right? And he said there must be something deeply hidden that explains why it's doing this mysterious thing. And he felt the same way about quantum mechanics, that we gave these set of rules, which are called the Copenhagen interpretation of quantum mechanics. One set of rules for when you're looking at it, one set of rules for when you're not. And Einstein was like, oh, come on. Clearly, this is not the final answer to the nature of reality, right? He wanted to know God's thoughts. He's like, I want to know everything. We're not done yet. There must be more going on. And so Many Worlds is one of the proposed answers to what could be going on. It's not the only one. There's alternatives, but it's definitely my favorite. It's definitely the easiest one to write down. Let's put it that way.
Okay, so hit us with this many worlds theory.
Okay, so think about this electron. You say that it could be either spin up or spin down. It's a combination of both. That's its wave function. You measure it, you only ever see spin up or spin down. So Copenhagen says that's because the wave function suddenly changed, snapped into place when you observed it. Don't ask me what it means to observe something. That's not what Copenhagen lets you ask.
Okay.
Many World says what you're missing is two things. Number one, you're a quantum system. You're obeying the rules of quantum mechanics. You're made of atoms and electrons and so forth. You have a wave function too, okay? So you're secretly treating yourself as a classical thing when you make that measurement, but you really should be treating yourself quantum mechanically, right? That's one thing. And the other thing is something that Einstein invented, namely called entanglement. When quantum mechanics says there's a wave function for a system, it doesn't say there's a separate wave function for every particle. Right? It says that there's only one wave function for the whole universe. So the way I like to say it is, imagine two particles come in and bounce off of each other. Either one has a wave function and it's unpredictable exactly what angle it's going to go off at. So both of the particles that go off, you don't know where they're going. But because momentum is conserved, if they came in at equal velocities, they'll go out at equal velocities and in opposite directions. If you measure one, then you know where the other one is going, right? That's entanglement. The observed state of one system can be related to the observed state of another system.
We have found a new particle never seen before in Mother Nature.
Something strange is happening at CERN, and world-renowned physicist Michio Kaku has raised the alarm. The Large Hadron Collider, the most powerful machine ever built, has been suddenly shut down, and whispers of terrifying consequences are spreading. From mysterious energy fluctuations to theories of reality-altering experiments gone wrong, scientists and the public are on edge. Could this be the start of a catastrophic event? Or is there more to the story than meets the eye? Stay tuned to uncover the chilling truth. Introduction to the Large Hadron Collider, LHC. The Large Hadron Collider, LHC, is a massive circular particle accelerator managed by the European Organization for Nuclear Research, CERN. Hidden under the Swiss countryside near Geneva, it stretches for 27 kilometers in circumference, so extensive that one could spend nearly 6 hours walking around its entire ring. Constructed between 1998 and 2008, the LHC began operation in September 2008 and quickly emerged as a pinnacle of modern experimental physics. At the heart of this machine lies an ambition to test fundamental theories about matter, energy, and the universe itself. Physicists like Michio Kaku and others have frequently drawn attention to the LHC's mission of exploring realms once confined to imagination. Designed to smash protons together at extraordinary speeds, the collider brings these particles to energies measured in tera-electron volts, TeV, a range that recreates conditions akin to a split second after the Big Bang. Before the LHC, many vital questions remained unanswered about how the cosmos formed and how tiny building blocks called quarks, leptons, and bosons fit into the standard model. Researchers hoped that the LHC would uncover new phenomena, including exotic particles or forces, and confirm long-standing theories about the origins of mass. One of the biggest milestones came with the July 2012 announcement of the Higgs boson discovery, confirming decades of theoretical work about a universal field that imbues certain particles with mass. Beyond pure science, the LHC has captured popular imagination. Some speculate on potential doomsday scenarios or worry about black holes, especially since the collider's early planning stages elicited concerns in various media outlets. Although top physicists generally dismiss apocalyptic fears, the LHC's advanced capability makes it a lightning rod for theories about cosmic catastrophes or the end of reality. Despite the hype, practical considerations underpin its construction. Placing the machinery underground offers natural shielding from radiation, reduces noise, and helps keep everything stable. Above ground, supporting equipment like cryogenics, radio frequency cavities, and magnets occupy specialized buildings. Below ground, hundreds of superconducting magnets cool to near absolute zero with liquid helium, guiding beams around the ring. This multinational project brings tens of thousands of physicists, engineers, and students together, using high-tech tools to sift mountains of collision data. Each year, the LHC's complex infrastructure processes about 15 petabytes of information, broadcasting these results around the globe. For many, the LHC symbolizes humanity's pursuit of ultimate truths, an attempt to peel back cosmic layers once hidden. Numerous breakthroughs flow from experiments at each crossing point of the collider ring, advancing understanding of how fundamental forces interact. With the machine's ongoing runs, scientists continue to refine their models of the universe, forging ahead in this age of high-energy physics exploration. Structure and functionality of the LHC. At its core, the LHC is essentially two accelerators in one. It propels two beams of hadrons, usually protons, but sometimes heavier ions, around a 27-kilometer loop in opposite directions. When these beams cross paths at designated interaction points and collide, an enormous number of particle events unfold. Tiny subatomic constituents spray out in all directions, and sophisticated detectors measure their properties. A key detail involves the time and effort needed to shape, steer, and squeeze the beams until the collision rate is maximized. Superconducting magnets, cooled by superfluid helium to negative 271 degrees Celsius, generate intense magnetic fields that keep each beam on a circular track. The initial injection often comes from smaller pre-accelerators, building up beam energy in stages. Once inside the main ring, the particles approach the speed of light, swirling hundreds of thousands of times around the loop every second. The beam energy reached 3.5 tera-electron volts per proton early in 2010, then rose to 6.5 tera-electron volts per beam after upgrades. This improvement nearly quadrupled the world's previous records, enabling creation and detection of phenomena that no smaller collider could generate. The ring itself is located underground, achieving depths from about 50 meters to 175 meters, weaving beneath the Swiss-French border in a meticulously planned route. Timing is everything in these collisions. Only at 4 key points do the two beams intersect. These points are flanked by monumental detectors called ATLAS, CMS, ALICE, and LHCb, each specializing in unique research areas. ATLAS and CMS handle broad-spectrum physics, looking for everything from the Higgs boson to hypothetical supersymmetric particles. ALICE delves into conditions replicated by heavy ion collisions, while LHCb tackles subtleties of matter, antimatter asymmetry. Proton-proton collisions are the norm, but the LHC also carries out heavy ion runs to generate quark-gluon plasma, paralleling the early universe's extreme conditions. Each time the particles slam together, a flurry of fleeting states and subparticles can emerge. Because many last only picoseconds before decaying, specialized detectors must pass and store these ephemeral signals in real time. In total, the LHC has 7 detectors spread around the ring, though the 4 named above are the largest. These experiments receive a fraction of the collisions that occur, capturing data on factors like energy, momentum, charge, and decay products. The analysis of collision events requires advanced trigger systems to decide which events are worth saving, given the high collision frequency. Construction and costs. The massive tunnel the LHC occupies was originally dug for a previous collider named the Large Electron Positron (LEP) Collider, constructed between 1983 and 1988. When LEP was decommissioned around 2000, CERN chose to reuse the tunnel for its new proton-smashing machine. This reuse helped reduce costs, but did not prevent an overall price tag of about €7.5 billion. By 1995, the project had been officially greenlit, allocating €2.6 billion plus significant extra funds for the experiments themselves. Despite extensive planning, getting the LHC operational proved challenging. On September 10, 2008, it switched on for the first time. Yet within just a few days, a magnet quench incident caused helium leakage and lasting damage, stalling progress for 14 months. Over 50 of the superconducting magnets required repairs or replacements. The intricate cooling infrastructure had to be rethought with improved safeguards and new safety measures. This major setback underscored the engineering difficulties involved in operating large-scale cryogenic systems and maintaining stable beams over extended periods. Nevertheless, the machine was repaired and restarted in 2010. At that stage, collisions reached energies of 3.5 tera-electron-volts per beam, setting an unprecedented record. Over time, further shutdowns gave engineers room to install brand-new superconducting magnets, update cryostats, and perfect other hardware. By April 2022, the LHC was ready to push the envelope again, with the stated goal of pushing beam energies up to around 6.8 tera-electron-volts, or slightly higher per beam during the third run. Funding for these upgrades and operational phases includes contributions not just from European nations, but also from observer states worldwide. In total, 10,000 plus scientists from over 100 countries rely on this machine for advanced research, ensuring a shared financial and intellectual commitment. The 15 petabytes of generated data each year are distributed globally, requiring an established network of computing centers. This scale of activity has made the LHC a focal point for both technological development and scientific progression. The cost also extends to mundane but crucial aspects, such as maintaining a vacuum inside the beam pipe. Even a minute contamination can degrade beam quality or damage sensitive equipment. Therefore, the entire ring is carefully sealed with advanced vacuum pumps and tight seals spanning all sectors of the tunnel. These engineering steps underscore why building and running the LHC costs billions, yet they enable a breadth of experiments that have redefined fundamental physics. Key discoveries and achievements. The LHC's operation is divided into distinct periods called runs, each lasting a few years. Run 1, which took place roughly 2010 to 2013, brought about major revelations. Topping the list was the July 4, 2012 announcement of the Higgs boson discovery, which is seen as one of the biggest scientific achievements of the 21st century. Researchers at the ATLAS and CMS detectors found signals that match predictions for the Higgs boson, effectively confirming the standard model framework that had guided particle physics for decades. Beyond the Higgs boson discovery, Run 1 also led to the creation of a quark-gluon plasma in heavy ion collisions with lead nuclei. This plasma is thought to mimic conditions of the universe microseconds after the Big Bang, allowing researchers to see how quarks and gluons behave at extremely high temperatures and densities. During this time, other important measurements included studies of certain bottomonium states, clarifying aspects of quantum chromodynamics, QCD, the theory of the strong force. Run 2, from around 2015 to 2018, opened the door to even more in-depth analyses due to doubled collision energies of up to 6.5 TeV per beam. In this period, scientists expanded research on Higgs boson decay modes, explored possible signals that could indicate physics beyond the standard model, and found an impressive number of new hadrons. By 2021, the collaborative efforts of experiments at the LHC had uncovered around 59 new hadrons. Many of them exotic states such as tetraquarks and pentaquarks, which further sharpened understanding of the strong interaction. Run 3 began in April 2022, following a 3-year break used for major maintenance and upgrades. Plans for Run 3 involve pushing collision energies slightly above 6.5 TeV and increasing the total number of collisions recorded. These efforts seek to collect enough data to refine measurements of known phenomena and potentially detect extremely rare events. One highlight is the renewed possibility of seeing new physics signatures that were too faint to detect in earlier runs. Another notable milestone occurred on July 2nd, 2022, with the announcement of a new pentaquark featuring a combination of quarks and antiquarks, including one strange quark as well as up and down quarks. By studying unusual combinations like these, scientists can test the limits of theories describing the strong nuclear force. Throughout these runs, the LHC's technology has proven flexible enough to accommodate a variety of beam. Although proton-proton collisions remain the main event, the machine can handle heavy ions or even proton-ion collisions for focused studies of nuclear matter. Each data set reveals something new about how particles interact under extreme energy densities. The synergy of 4 major experiments, ATLAS, CMS, ALICE, and LHCb, has unraveled phenomenon after phenomenon across the subatomic world. Heavy ion collisions by ALICE created fleeting droplets of quark-gluon plasma. Rare decays, studied by LHCb, probed the matter-antimatter imbalance, while ATLAS and CMS looked for exotic particles that might provide clues about supersymmetry or dark matter. The Higgs boson and its significance. Among the LHC's defining achievements stands the discovery of the Higgs boson, revealed on July 4, 2012, to the excitement of physicists worldwide. The late 20th century had seen theoretical proposals of the Higgs field, a pervasive energy field that slows certain particles, giving them mass. Without this mechanism, particles would remain massless, and atoms, molecules, and everyday matter would not form. When the LHC's experiments recorded a distinct peak at around 125 GeV per c squared, consistent with Higgs boson predictions, it confirmed a critical pillar of the Standard Model. The boson was understood as an excitation of the Higgs field, like a ripple in a cosmic ocean. This validated the idea that the observed mass spectrum of particles arises from their interactions with this field, not from an ad hoc assignment. Physicists Peter Higgs and François Englert received the Nobel Prize in 2013 for contributions to the theory behind this discovery. Yet the story does not end at simply spotting the Higgs. Ongoing questions include whether the Higgs field might connect to scenarios involving dark matter or hidden dimensions. Some even worry about false vacuum states, where the Higgs rests in a local energy minimum that could, in principle, decay. While theoretically conceivable, any cosmic shift from a false vacuum to a deeper ground state is considered extraordinarily improbable on human timescales. Crucially, the Higgs boson's measured properties keep matching the Standard Model's forecasts, though minute deviations could hint at unknown physics. That is why the LHC continues to gather more data. Scientists always look for anomalies that might crack open new theoretical directions. Even slight variations in decay probabilities might point to advanced theories like supersymmetry or show how the Higgs couples to heavier particles. Moreover, the Higgs has broader meaning for the formation of structure in the universe. Soon after the Big Bang, if the Higgs field had behaved differently, matter might never have coalesced into atoms and galaxies. Essentially, life owes its existence to a cosmic synergy that includes the Higgs mechanism. By directly observing and cataloging the boson's behaviors, researchers aim to refine their comprehension of the cosmos' earliest eras and the fragile balance that allows mass-based life forms to thrive. Furthermore, the false vacuum idea arises when discussing the Higgs field. Some physicists suggest the Higgs field might not be in a true ground state, but a local minimum, meaning it is stable on cosmological timescales. yet theoretically capable of tunneling into a lower energy state. If that occurred, it might reshape the entire universe in a wave of destruction. But the timescale for such a hypothetical event is so long, far exceeding the 13.8 billion-year age of the universe, that it does not create immediate worry. Magnetic field crack incident. Amid the excitement surrounding Run 3, a separate phenomenon on July 7, 2022, captured public attention when a crack in Earth's magnetic field remained open for 14 hours. Ionized solar wind poured in, triggering a geomagnetic storm that produced stunning auroras, visible in parts of Canada and the US. Coinciding in time with the LHC's upgraded run, the event fueled speculation that high-energy collisions might have somehow destabilized Earth's magnetic shield. However, space weather experts attribute such cracks to co-rotating interaction regions, CIRs, emitted by the Sun. Similar to coronal mass ejections, these CIRs compress and disturb Earth's magnetosphere, occasionally creating temporary vulnerability. Historically, NASA researchers have described our planet's magnetosphere as somewhat drafty, forming sporadic windows that allow solar wind to penetrate. The July 2022 crack, open far longer than typical, underscores the dynamic nature of solar particles colliding with Earth's defensive shield. Scientists from groups like NOAA classified the resulting geomagnetic event as relatively moderate, with enough intensity to paint the skies but not severely disrupt satellites or power grids. Nonetheless, the prolonged opening gave watchers in northern latitudes a front-row seat to vivid auroral display as swirling colors danced across the horizon. The unusual timing, lining up with the LHC's busy schedule, led to rumors tying these two events together. Skeptics of the official scientific stance pointed to the LHC as a possible trigger, linking its intense power usage and high-energy collisions to global-scale phenomena. Experts, however, dismiss such notions, explaining that no known mechanism exists for a collider operating underground to precipitate large magnetic tears in Earth's protective layer. The energies involved, though huge on human engineering scales, are small compared to cosmic rays hitting Earth's atmosphere daily. Nevertheless, the magnetic field crack event provided fresh fodder for doomsday headlines and conspiracy theories about the LHC. Because the storm was visible and the timing intriguing, social media chatter ballooned. In the end, data from solar weather monitoring specifically tied the crack to solar wind stream, showing no correlation with the collider's operations. Ultimately, the swirling auroras became an aesthetically pleasing byproduct of typical solar-Earth interactions, rather than a sign of meddling by high-energy physics. Theoretical risks and concerns. Whenever a project like the LHC pushes scientific boundaries, questions arise about the potential risks. One concern is the idea of a false vacuum scenario triggered by high-energy collisions. If the Higgs field suddenly tunneled to a lower energy state, the consequences could, at least in theory, be catastrophic. The entire vacuum structure of the universe might transform, erasing existence as we know it. Yet scientists note that cosmic ray collisions in outer space already surpass LHC energies. If a false vacuum event were that easy to ignite, it probably would have happened long before humans built colliders. Another worry is the creation of miniature black hole. In principle, known physics does allow for gravitational and quantum effects at extremely high energies to produce tiny black holes. However, such miniature black holes, if formed, would either evaporate almost instantly via Hawking radiation or remain benign on micro scale. Nature produces collisions at or beyond LHC energies pretty regularly in the upper atmosphere, generating no doomsday black hole. This consensus is backed by papers published before the LHC was even built, analyzing theoretical black hole production and concluding no threat exists. conspiratorial ideas also pop up. Some claim the LHC could open portals to other dimensions or serve as a government conspiracy to manipulate global events. Internet narratives sometimes associate the collider with predictions about the end of the world, top-secret mind control, or unleashing demons from alternate planes of reality. Scientists find these rumors unfounded, as there is zero evidence for such phenomena. Real experimental data show the byproducts are subatomic particles consistent with known physics or slight variations that require more study to unravel. From a practical standpoint, the LHC does have safety protocols. The magnet quench event in 2008 highlighted how vital it is to manage superconducting magnets and cryogenic systems carefully. Engineers introduced robust sensors and emergency venting mechanisms to prevent future large-scale damage. Regular maintenance shutdowns, such as the ones in 2013 to 2015 and 2019 to 2022, involve thorough inspections to ensure the equipment runs smoothly. Public outreach by CERN focuses on explaining the science behind the LHC, its potential to revolutionize our understanding of forces and particles, and why certain doomsday scenarios are not scientifically grounded. The underlying physics tells us that if truly cataclysmic events could stem from energies in the TeV range, we would likely have seen such events triggered naturally across cosmic history. Upgrades and future plans. The LHC was always planned in stages to let scientists improve its capabilities over time. Soon after Run 2 ended in 2018, the machine entered a long shutdown to prepare for Run 3. This new run, starting in April 2022, involves collisions at around 6.8 tera-electron volts per beam and better detection systems that can handle higher collision rates. The upgraded hardware allows more collisions to happen each second, higher luminosity, increasing the statistical reach of searches for rare processes. One major effort is known as the High Luminosity LHC, HLLHC project. Initiated in June 2018, it aims to raise the collision rate even more, going beyond the LHC's original design. Expected to become operational around 2029, the HLLHC will gather data at a rate 10 times higher than the LHC can manage at present. Such an increase will help researchers refine measurements of fundamental constants and search for subtle effects that occur too infrequently for current sensitivity. Looking further ahead, there is mention in the physics community of a possible future circular collider, FCC, that might someday replace the LHC ring with a more than 80-kilometer circumference tunnel capable of reaching energies even greater than the LHC's possible 14 TeV limit. Those plans, however, remain in conceptual or early design stages. Between each run, careful planning is required not just for hardware, but also for the software and computing infrastructure. As the collision rate climbs, the data volume skyrockets, requiring new developments in machine learning, real-time data analysis, and distributed computing. These expansions must be completed before the next run can start so that the experiments do not drown in data they cannot analyze. During the scheduled shutdowns, elements like the superconducting magnets get replaced when needed, and new technology is installed in the detectors to cope with higher event rates. For instance, the ATLAS and CMS collaborations have been reinforcing detectors to handle more collisions per bunch crossing, while also enhancing their ability to measure subtle signals above background noise. Meanwhile, ALICE is refining its systems to further study quark-gluon plasma in heavier ion collisions. Overall, the LHC's future is about pushing technological and scientific boundaries. Despite occasional rumors that the collider might shut down early, it is more likely to continue operation well into the 2040s as each upgrade cycle extends its scientific reach. These plans ensure that the LHC remains a premier site for discovery, bridging any gaps between known physics and the unknown phenomena that might still be out there. speculations, and conspiracies. Ever since the LHC was proposed, there have been wild rumors. Early on, some tabloids claimed the LHC was a black hole machine that would swallow Earth. Others tried to connect the collider with ancient prophecies about the end of times. More recent conspiracy theories revolve around mythical beliefs, suggesting that the LHC's collisions open portals to other realms, sometimes portrayed as demonic or sinister. A popular web-based rumor spread photos of the statue of the Hindu deity Shiva, displayed at the CERN grounds as a gift from India, tying it into baseless ideas about worshipping destructive deities. In truth, the statue was meant as a cultural symbol of cosmic dance, representing the interplay of creation and destruction in the universe. Fitting metaphors for particle physics, but not evidence of dark rituals. Some go further, suggesting the LHC is a secret government tool for mind control or weather manipulation. They point to occasional timing coincidences between LHC experiments and events such as unexpected storms, or, in July 2022, the previously mentioned crack in Earth's magnetic field. Scientists categorically reject such connections because they lack any plausible physical mechanism. Additionally, claims have emerged that the LHC might cause large-scale changes in the Higgs field, unleashing unstoppable cosmic transformation. While there are scientific discussions regarding the Higgs vacuum state, these revolve around probabilities so remote that they are practically zero over billions of years. Indeed, cosmic rays hitting Earth at energies higher than LHC collisions have been happening for eons, with no sign of vacuum collapse or dimension-ripping cataclysms. Many conspiracies feed on the sense of secrecy or complexity that surrounds cutting-edge physics. The LHC's technical equipment and jargon can be intimidating to a lay audience, leading to misunderstandings or oversimplifications. CERN openly addresses these rumors, emphasizing transparency in operation details and scientific results, which are shared worldwide through research papers and open data programs. Broader implications. The LHC's broader implications extend well outside the realm of pure particle physics. Every improvement in hardware or software fosters technology that can be applied in medicine, computing, and engineering. For instance, advances in superconducting magnet technology contribute to more powerful and efficient MRI devices in hospitals. Data analysis methods developed at CERN, including distributed computing frameworks, find uses in weather forecasting, climate science, and complex simulations across industries. The discovery of the Higgs boson underlined the triumph of collaborative, global-scale science. This success story has inspired large-scale initiatives in other fields, such as space exploration missions and multinational biomedical research projects. Governments and funding agencies often cite the LHC as a prime example of how basic research can yield transformative knowledge and technologies. The collider is not just a single laboratory's achievement, it's the fruit of 10,000-plus scientists, technicians, and students worldwide, all contributing ideas, designs, and labor. As more runs are completed, the LHC could uncover new forces or reveal pathways to understanding dark matter, which makes up roughly 27% of the universe's mass energy content. Researchers are eager to see if collisions produce exotic particles that could explain the gravitational effects attributed to dark matter. Some models hint that if the LHC cannot see these particles, a future generation of colliders or a different type of experiment might be needed. Regardless, the LHC's results guide the search by ruling out certain masses or interaction strengths. Another area of interest is whether the LHC might detect evidence for extra dimensions. A variety of theories, including string theory and brane world models, require more than the familiar 4 space-time dimensions. If additional dimensions exist at scales just beyond current detection limits, LHC collisions could show anomalies in how energy and momentum appear to vanish. So far, no conclusive evidence has emerged, but the quest remains one of the collider's most captivating draws. Furthermore, the heavy ion collisions replicate conditions akin to the early stages of the Big Bang, allowing researchers to study substances like the quark-gluon plasma that existed at tiny fractions of a second after the universe was born. This helps piece together how matter first coalesced from the intense heat of that era. Behind these physics goals is a recognized principle of incremental progress. Each run 1, run 2, run 3, etc., gathers more data and offers sharper experimental precision. Technologies introduced in the upcoming Run 4, beginning around 2029, will likely increase collision rates by an order of magnitude, resulting in data sets big enough to expose extremely small effects or even brand new phenomena. The LHC's presence also stimulates educational outreach, with many universities worldwide offering courses or degrees centered on particle physics research at CERN. Graduate students who work on these experiments learn not just advanced physics, but also data science, engineering, and problem-solving on a grand scale, experience that can later be transferred to diverse fields. Thanks for watching another episode. While you are still here, make sure to click the video on your screen for more quality content.